Imagine that we are going to have now a ring, and this ring is charged electrically, and we're going to generate it once again for a positive charge, although the negative charge, once again, is going to be exactly the same procedure, but the only situation that is going to happen is that the direction, or sorry, the sense of the electric field is going to change. So if we have a positively charged ring and we calculate the electric field at point P, which is a point located at a distance x from the center of the ring, what is going to happen is that, for instance, if we have a differential here of charge, any given differential, this will actually exert an electric field that goes out of the ring, and it will generate an electric charge here. And for instance, an opposite point or differential of charge here will generate an electric field of the same magnitude. The direction changes, but then the y-axis here, the y component of this guy and the y component of this guy are exactly the same, and they will cancel each other. So actually, at the very end, all the contributions will actually generate a vector of electric charge which points towards the positive x direction, and this is going to be the electric field, and it's only defined in x. The distance that is going to be from any given point towards the point where we are evaluated is going to be the radius, and we call this r, the radius r. And well, we have the radius of the ring, and the radius of the ring, I am going to call it a. Okay, a is the radius of the ring. The distance is the radial distance from the point of charge and the point we're evaluating the electric field, and well, this is an amount dq. We generate the integral of the electric field, since it's a continuous distribution, and this integral equals well, is going to be the integral of k dq over r squared, and the unit vector, the unit vector, which is the direction. Well, since it's the x direction, this unit vector is going to be x over the hypotenuse, which is, for instance, a squared plus x squared, square root of that. Just remember that, for instance, if we have a vector that goes towards this direction, right, and y is towards this direction, and towards this direction it goes x, and this is, for instance, a squared, well, y squared plus x squared, square root of that. If we only want the component x here, the component x is going to be given as, for instance, if we had theta, the component x, which is the green one, is going to be the vector, right, y squared plus x squared cosine of the angle, such that the cosine of the angle is x over the hypotenuse. And that's the reason why we have this unit vector, which is x over the hypotenuse. And well, k is constant. The radius, which is the distance, is constant, and this radius is given once again by the radius of the ring, which is a squared plus x squared, the square root of that. and we have it to the square, so we have, for instance, a squared plus x squared, that's constant. X is constant once again. The square root, this square root is going to be constant as well, so this will make this amount to the 3/2, right? And then this is the integral of dq. And the integral of dq is q. So the electric field at a point P, which is located at the center of the ring, but upwards, for instance, if you have a ring, it's upwards or downwards, is going to be equal to kx over the radius of the ring plus the distance from the center towards the point we're evaluating to the 3/2 times the charge. And this is the electric field of a ring. We're going to use that later on.